So this is the Pendulum lab, and what I had is each like groups 1, 2, and 3. I want to know, how does the period of a simple pendulum depend on the mass of the pendulum, holding the length and amplitude fixed? And then group 4, 5, and 6, how does the period of the simple pendulum depend on the length? And then 7, 8, and 9, how does it depend on the amplitude? And when you take data like this, I want the smallest value that you measure to be at least 1/5, or I want the biggest value to be at least 5 times greater than the smallest value, so you can see any mathematical patterns that come up. Okay, so make sure you write up your procedure for it, and then you're going to need a data table. I want your data table to be very easy to understand and read. Everything's labeled. If I look at the steps in your procedure, it should, feed directly to what's in the data table. Then you were to graph your the period as a function of either mass, length, or amplitude. Okay, and you'll collect data. Now, and then we're going to analyze it. And what I'm going to do right now is the consensus. And I'm going to have to go through this, unfortunately, faster than I normally would. So if you graphed the period as a function of the mass, this might be in seconds, this is in kilograms, you might have gotten something like this. Okay. And I think some of you did. Now, here's what you're really tempted to do, and I saw some of you doing this. You expand the vertical axis. I don't want you to do that. Don't ever do that in this class. You want to just leave it as it is. Yeah, there's going to be a little variation because you're not perfect measurers of time, or there's little deviations in it. But what you should have seen, yeah, that's fine. What you should have seen is that really, no matter what the mass is, if you keep the length and the amplitude constant, you should have seen the period not vary much at all, if any. In other words, the period does not depend on the mass. Okay, so the period, so you need to write that out. Then group 7, 8, and 9, the period in seconds, and then you had different amplitudes in, I don't know, centimeters. Whatever if you use meters, that's fine. And what you should have seen is it's just like this. It might vary a little bit, but overall, if you don't expand this out, you won't see a pattern other than just a horizontal line. Because it turns out that the period of a pendulum does not depend on the amplitude. It really doesn't. I think you guys had that, group 9. I think you saw that very clearly. I didn't see your whiteboards, but that's what you should see. But the length, it did matter. So I'm going to use this group's data, and then we'll graph it real quick, and hopefully it'll be good. So the we'll graph this period in seconds, length in we'll go ahead and change them to meters. You have them in centimeters. So for length in meters, here's what you had: 20, 40, 60, 80, 100. Well, 0.2, 0.4, 0.6, 0.8, and 1.0. And here's the here's the period that you measured. 0.905. 1.26. 1.55. 1.78. And then 1.995, I'm just going to call that 2.00. Now if I were to graph this, I'm going to go 0.2, 0.4, 0.6, 0.8, 1.0. And then this is going to go from 1 to 2, so I'm just going to, here's 1 second, here's 2 seconds, so 0.2, 4, 6, 8, 10, 0.2, 4, 6, 8, 10. So this is 1.0, 2.0. Now I'm going to graph these. At 0.2, it's 0.905. So, this is 0.2, 0.4, 0.6, 0.8. So at 0.2, it's 0.95, 0.905. So that'd be right about here. At 0.4, it's 1.26. So here's 1, 1.2, 1.26 would be right about there. Well, that's nice. This is good data. And then at 0.6, it's 1.55. So 1.2, 1.4, 1.55 would be right about here. At 0.8, it's 1.78. So 1.2, 4, 6, 7.8, somewhere around in there. And then at 1.0, it's 2. Now it looks kind of straight, but and this there might be a little error, but I'm just going to cut to the chase here. It's going to look something like this. It's not linear with the length. So, so what does this look like? Well, watch this. This is really amazing. A graph that's this shape looks like a square root function. Well, it's like a parabola on its side, which is what a square root is. So I'm going to plot. So I'm going to say, hey, maybe the period is a function of the square root of L. So I'm going to get the calculator out. 0.2. What's the square root of 0.2? It's 0.447. What's the square root of 0.4? It's 0.632. What's the square root of 0.6? It's 0.775. What's the square root of 0.8? I get 0.89. 894. And then what's the square root of 1? 1. Okay, so if the period is a function of the square root of L, we should get a graph that's a little different. So let's graph it. We should get it. It should come out to be linear. So L goes from 0, or square root of L goes from 0 to 1. So it's almost the same as this point. 2, 4, 6, 8, 10. And this is the square root of L in the square root of meters. And then this is just going to be period in seconds, and it's the same. 0.1, 2, 3, 4. 1 second. 1, 2, 3, 4. 2 seconds. And so at 0.447, we have, it's 0.905. So 0.447, so 0.4, here's 0.5, so 47 will be in between, be right about there. And the period is 0.905. So here's 0.9 right there. And 0.632, 0.6, here's 0.7, 0.632 to be right about there. And this would be 1.26, 1.2, 1.4, 1.326 would be right about there. And then 0.775, here's 0.775 would be right about 3/4 of the way over, so from that. And it's 1.55, so 1.2, 1.4, 1.55 would be right there. .894, here's 0.8, 0.9 to be slightly less than that. Remember, this is just a hand sketch, but it works pretty good. And 1.78, so 1.2, 4, 6, 7.8, so right about there. And then at 1, you get 2. Now look at this. These line up, even with the origin. It's a straight line. So that means, if this turns out to be a straight line, that means that the period is indeed a function of the square root of L. Now if it wasn't, if I guessed wrong, this wouldn't line up so well. So let's take a look at these data here. Y equals mx plus b. Instead of y, this is the period equals. Now what's the slope of this line? We're really short on time because we have one more thing to do today. So you see that if you go over 1, you go up 2. So what's the slope? It's just 2.0. And what are the units for that slope? Rise over run, seconds per square root of meter. And then what is x? The x is the square root of L. And what is b? Well, these lined up, went right through the origin, so it's 0. So this is a function for the period as a function of the square root of the length. Watch this. This is truly astonishing. This is, I mean, I fudged it a little bit, but this is based on data that was taken by you guys, or one of the groups. So this turns into this. This is derived from data. I didn't make this up. But what did we say was true early on about the period of a simple pendulum? I gave you this formula. Right? Now watch this. This is, I love doing this. This is 2 pi times the square root of g times the square root of L. You see what I did there? I just took this and separated the numerator and denominator. Why did I do that? Well, because these are constants. So this is 2 pi times the square root of 9.8 meters per second squared times the square root of L. Well, let's evaluate this. 2 times pi divided by 9.8 raised to the 1/2 power, or the square root of it, and you get 2.00. You get 2.00. This is equal to 2.0. And what are the units? Well, if you look, it's 1 over the square root of meters per second squared. Well, this reciprocate and multiply. This becomes seconds over the square root of meters. Now this was based on theory that we discussed earlier. This is based on data, empirical data. Whoop, it's the same. It's pretty awesome. It works! So, and take a look at this equation right here. Right here. Look at this one. Notice that in this equation that describes the period of a simple pendulum, there is no mass. It doesn't depend. The period does not depend on mass, and that's what you found, really. If you look at your data carefully. And this period does not depend on amplitude. But it does depend on the length. And here's the relationship we found empirically, and here's the relationship that theory gives us. It's the same. That is all.